So here we are. This is the last class of 127. And I decided to present material on the last day because I think it's interesting. Some of my other classes I didn't. But we're going to talk about source code auditing. And so I've got some slides here. And yeah, that's right. Extrapolated privacy. That's the problem. There's no privacy in the Constitution. They chose to extrapolate the amendments to deduce privacy, and that has apparently now been abandoned. So everything that depends on privacy is going to have to be explicitly written into a law. Anyway, so however, before this, I wanted to answer a question that came up last time. Someone asked, how do you have a Stack Overflow and you hit the structured exception handler? And so I tried it, and let me just demonstrate this. It turns out to be pretty easy to understand. So let's do debug, restart. Come on, I say, this thing listening to me? Debug. Oh, I remember, perhaps my Windows is going to be too slow in responding to be useful when streaming. This happened to me before. I'll just look at the slides. I have forgot that live demos are counterproductive when running a local virtual machine. But it's finally moving just when I give up. I'll give it a try. Debug, restart. Okay, good. All right, and then run. So this is the project with the structured exception handler overflow. So here's the code. I just send it 3,551 A's, followed by BCDE, followed by a lot of X's, enough X's to make a total of 4,000. So I send them that. And if this thing will respond, instead of just popping up the stupid Windows Start menu covering everything. No, looks like it was not running. All right. All right, we're going to look at the slides because the stupid Windows demo is so slow it's useless. So, all right, so you send A's followed by BCDE followed by X's with this program, and you will then overflow into the exception handler. And if you look at viewing the exception handler, you'll see here's the A's, 41 to 41, then the BCDE, and here's the address of the first exception handler record. And this is F3F FCC. If you look at the memory map, F3F is here. That is the stack of one of the threads. So it's on a stack, apparently of the thread handling this process, and you can see it. If you just go back into the CPU window of the Immunity Debugger, you can see the stack here. So here's some return pointers to go back from some function. And here is the stuff that was sent from that program, the beginning Gmon stuff, and then here's all the A's. And if you just scroll down to the bottom, here's the A's, then comes BCDE, and then the X's, and the exception handler is just sitting on the stack, right, like everything else. So I was unable to find any good explanation anywhere of why the exception handler is placed on the stack, but apparently it is put there. So I guess the exception handler is handled frame by frame or something. I don't quite understand why it's on the stack, but it is just sitting there on the stack. So filling the stack with junk will hit it. So anyway, that's an issue that came up last time and I didn't have a good answer. So that's the amount of information I was able to figure out about it. So anyway, let's talk about source code auditing to defend yourself against the sort of attacks we've been doing all semester. So this is often the best way to find vulnerabilities. It's one way, it's not the only way. And you can just search through source code with a text editor and grep or something, but of course there are tools that will automate that process and try to help. Well, yes, it was in fact in the current stack in that exploit. And that's an interesting issue. I don't know if there's always an exception handler in every stack. Maybe there is. So CScope was a source browsing tool that people say they like it if you're going to look for something huge like the whole Linux kernel. CTags is another one that makes tag files to try to help you search through large code bases. I haven't used these, I don't know what your book tells us about them. Anyway, you can just use any text editor you like. Most text editors will at least have colors so you can find matching closing braces to match your opening braces, which will help you interpret code. And there are others, tools that may do a lot more to help you. Like Splint is one that was supposed to be a way to do static checking of code, but very badly out of date. And there are a lot of others, typically specialized by language, which makes sense. I mean, every language would require its own specialized tool, logically. CPP check is one that you can install on any Debian-based system and run. I was not pleased with it, although I must say, one of my consulting gigs, they're using an expensive source code scanning tool, and the thing is terrible. It's finding about 10% of the vulns it should be finding. They tend to be awful. They tend to miss everything. So I had this one written up as a project at one time. You can easily put it on Kali Linux, but I didn't think it was worth doing because it's so ineffective. So here's a heap overflow, one of the ones from your project. It says you have two objects created on the heap, and then you overflow one and change it, and it detects nothing but memory leaks, which is a minor performance issue. It doesn't find the security flaw of the heap overflow. And if you have a format string vulnerability, which is incredibly obvious, you print buffer without any format string, it doesn't find it. It doesn't complain. It says buffer overrun possible. Well, it's true, it's also, but it doesn't find the format string, which is, this would seem like the easiest thing to find. You print something. Yes, these are incredibly straightforward vulnerabilities, especially the format string. You just flag any print F that only has one argument that's not an immediate string. You could do it with grep. It's incredible to me that these so-called security scanners cannot find the simplest thing. And the commercial one I used could not find a simple SQL injection. It's just sitting right there. It's appalling. Almost makes me want to write one, but I assume there must be some good reason they're so terrible. Anyway, Flaw Finder is one I found you can install on Kali that's much better at finding the vulnerabilities here. It really did find most of the vulnerabilities in the code we've written for this class. So that's somewhat better anyway for the simple code we've been using, although I don't know if it's going to be that useful in practice. Anyway, so you can look for specific lines of vulnerable code like format string errors. That's one way to go. And then, of course, you don't have to understand much about the application. You're looking for an error that is all on one line. The problem is a lot of vulnerabilities are not just from one line of bad code. So the other way is a bottom-up approach where you read large portions of code and try to understand it all, and then, of course, you can find more subtle bugs, but it's a lot more work. So most people do is a selective approach. They try to find code that can be reached. They work from the inputs. So you find whatever code handles the data that comes in from the input and just see if that code has a mistake, and you don't bother with the rest very much. Because that way you're trying to find the exploitable vulnerabilities, not every possible vulnerability. So here's the vulnerability classes. Generic logic errors are where you make some kind of fundamental mistake. A lot of these, especially in web application vulnerabilities, come from the translation from one language to another. For example, this is one that Dan Kaminsky and Moxie Marlinspike independently found at Black Hat and DEF CON a few years back, which is pretty awesome. The let's see, is this task on the code developer? Does the code get passed to another team? In practice, typically another team. I don't know anybody that actually expects their developers to write secure code, except I have heard that Netflix does, but everybody else passes it over to a security team, as far as I know. There are people that would like to change that, but that is the current flow that I've seen. So this is an example of what really happened. You could buy a certificate online, a digital certificate for an HTTPS site, and that was using really old code. It was using Pascal-based code. Now, in Pascal, strings are stored as a series of bytes, but you do not put a null byte at the end. Instead, at the beginning, you put a byte which specifies the length of the string. So every possible byte is a valid character, including the null byte. So you can make a string that has a null byte in it. So you could buy this certificate, starnull.evil.com. And in the language Pascal, that is a perfectly valid string, and they will sell your certificate to that domain. Now, your browser was written in C. So your browser when you go to a website, checks to see if a certificate is valid. It says, is the certificate from a trusted registration authority? Is it within the valid time period? And does it match the domain name? And so when I take this certificate and I sign, say, paypal.com, it will pass that test. It'll say it's from a trusted authority, which it is. It's within the valid date range. And to see if it matches paypal.com, it will take paypal.com. Does that equal this string? But this string is star. The null byte will terminate it, so it's a wildcard, so it will match any domain. So if you buy a domain name, a certificate like this, you can sign any website with it, and it will pass the test of HTTPS in a browser based on C, which they all are. And if you ask where's the bug, there's no bug. Every code, this code is working as intended, this code is working as intended. Nobody is going to have a CVE or an update or a bug to fix this. They both did their job correctly, but the end result is a disaster. That's the kind of subtle flaw that is not like one bad line of code. And so the kind we did in this class, they say they're almost extinct, where you just have simple buffer overflows, where you copy memory and such. Copy a large thing into a small thing to make a buffer overflow. That's the original LFX, LFNull buffer overflow, and those are not that common. That used to be the most common kind of vulnerability. Stack corruption is the blue ones here. You see, that was pretty hot, and it began to go down around 2010, around Windows Vista, when Microsoft put on these strong defenses like ASLR and DEP. And after that, it's become quite rare. What has gotten really big is heap correction stays pretty big, and use after free rose quite a lot, up through 2013 when Microsoft published this information. So there are other vulnerabilities, and in defenses, address space layout randomization and data execution prevention, there are ways around them. One way is to find a DIL that doesn't have ASLR turned on. Find an information disclosure to find out what address you're in. Here's return-oriented programming, the big one, the one we used in this class. And then heap spraying, which no longer works in modern browsers, which is why I took that project out. But heap spraying is where you attack a browser and you write JavaScript code to just make thousands and thousands of copies of your exploit in memory. So you fill all available memory with copies of your exploit, and then you just jump at random. And since you have a large NOP sled like 10,000 bytes followed by your egg, the odds are very high that you will hit some one of those NOPs. That's a heap spray. That's a way to overcome address space layout randomization. You don't need to know where your code is. You just fill all the RAM with your code. And then, of course, format strings. So a code audit could easily find it, although for some unknown reason, CPP check can't do it. And this one place people often find this is in code writing to log files, because log files can typically have a sloppy, clumsy format and nobody cares, so they'll just print something without a proper format. But of course, it's only vulnerable if the attacker can control the format string. And but that's been the case frequently. Then there's incorrect bounds checking, where you try to limit something like the length of a string, and somehow you do it incorrectly, so you get the wrong length. Here's a snort vulnerability from 2003. It has a series of fragments, and it checks each fragment to make sure it's not bigger than the buffer, but the problem is it's the total size of all the fragments that should not be larger than the buffer, and it didn't do that. Here come fragment lengths, and it checks to make sure length is greater than size, but that's the length of the current fragment, not the length of all the fragments. And by the way, I don't have the code for it, but I think the famous ping of death was the same. The ping of death was an individual ping, which you put more than 65,536 bytes of data in the ping, so it would be fragmented into many packets reassembled at the other end, and when they were reassembled, they would overrun the buffer and cause, I think, Windows 95 to crash. Anyway, then there's loops. Coders often have lots of loops and if statements within loops, and it leads to complicated situations. And there was one in sendmail that led to this. And the issue here was, this is the sendmail, that there were certain characters. Yeah, that was the ping of death. And so the sendmail was an email attack, and the point is it had this complicated code that would try to count how many characters there were in something, but there are some characters that count special. And I think the point was, if you send all these greater than and less than characters, those are interpreted as meta characters by part of the code, so they don't count towards the length, but they do end up getting stored. So the calculation of how long it is wrong, and you're able to overrun the buffer. That's the sort of thing. And we'll see quite a few that work that way. Then there's OffByOne, which is very common, where you don't calculate the length of a string correctly, like you forget about the null byte at the end. And so for example, here's an Apache vulnerability. You have if certain conditions, and here's if something else, more conditions. Then you calculate the length, but if you add these two lengths together, you're 1 byte too small in the allocated space because they forgot about a null byte or something like that. So under certain conditions, they allocate the wrong amount of length, and then they write the memcopy down here will write 1 extra byte out of bounds. And that, by the way, is the vulnerability that one of my students used to find the new jailbreak from a few years back on the iPhone. Became the check rain jailbreak. He found a flaw in the heap handling in the boot up sequence of the iPhone that made it possible to write 1 extra byte out of bounds, and that byte had to be a 0. But that was enough. He was able to gain complete control of the phone through that. And OpenBSD had an FTP daemon, and you'll notice here it goes through size of end path, processing things, adding the characters, but then if it's a quote, it adds an extra quote to the end. And the problem is they didn't consider how that affected the length. So if the last character is a quote, it will add that, and it will go out of bounds. And string, now you should not be using string cat anymore, which copies a string. You should be using string ncat, which string ncat, you specify how many characters to copy, but still it's messed up because it handles that stupid null terminator at the end in C. I really wish C used Pascal strings, but it doesn't. It uses C strings that always have an extra null byte at the end. And so if you copy with string ncat, 1 string to the other with the size, you can easily end up copying something that does not get the null byte. So you end up with a either writing out of bounds or getting a string that is not properly terminated, so it includes extra bytes that were not supposed to be in the string. So when you use it, you have to tell it how many bytes to copy, and you have to consider the null bytes. So if you don't terminate a string with a null, then the string will just continue, including all the readable bytes after it, all the bytes until it finds a null byte. So your string will suddenly be much longer. And if you write to that string, you'll be able to write to memory that's outside the space allocated for the string buffer. And that can lead to code execution, as we've done quite a lot here. An arbitrary write can easily be used to get control of the machine. So string ncopy, if there's not enough space in the destination buffer, it won't null terminate the string. It tries to write a null at the end, but if you tell it not to, that is not within the n bytes it's writing, it won't write the null. So here, the first string ncopy will not null terminate this, and therefore the second copy is not safe. First you copy into a buffer, and it doesn't put a null byte at the end, so when you copy it again into another buffer the same size, this one can overflow, because that one didn't have the null byte terminator and will therefore be bigger than you think it is. So you'd have to add this line. You'd have to make sure and put a null byte at the end of the first one to make sure that it's not longer than you think it is. And this is the kind of subtlety that many developers will not realize. All right, another problem is when you're reading a string, you don't always read it byte by byte. If you jump ahead by more than 1 byte, you might jump over the null byte. And that has happened a bunch of times. For example, here's Apache. If it finds a colon in a URL, it assumes that it's followed by 2 slashes. So it jumps ahead by 3. So here you go, skip the colon // move ahead by 3. Now that would be fine, except the colon is not always followed by // There are conditions. Here's the schemas that are common. There's ones like LDAP, news, and mail to that have a colon and don't use the //. So jumping ahead by 3 is not correct, and you can jump past the end and skip the null byte, and then you're going to keep processing stuff that was not really in that string. And then, of course, the sign comparison flaws. This is the famous one. It happens in almost every language. You use all the different kinds of numbers. So if you use a signed integer for length, then it can be negative. That's why there are exploits that involve a long string can't get in, like a string bigger than 100 characters. So you just have to make it really strong, really long, like 35,000 characters, and that will be interpreted as a negative length and get through. And there are other examples. Here's one in Apache, where they have buffer size, and remaining is the chunk size, and length to read should be the smaller of the two. So it sets the length to read. That's what this does. This is an if, and then sets it equal to r remaining. This will choose the lesser of the two, but the problem is you can have a negative chunk size. And so it will be interpreted as small when it's in fact large, because you used a signed integer where you should have had unsigned for all of these, and C will cast it to unsigned later. That's why it's in PHP, you have to use 3 equals if you want to compare things for security, because that makes sure that the thing on the left is equal to the thing on the right in value and in type. So it doesn't just cast one of them into a different variable type to compare them. In C, it's another, that can happen. And here's the kind of integer conversions. So 16-bit signed. If you give it -1, that'll be that'll write like this. This would be interpreted unsigned as 4 billion, or signed as -1. And so you got here's other ways to do it. If you have 16-bit signed and you cast it to 32-bit unsigned, it will be preserved. But anyway, there's things here. This -1 will turn into plus 65,000 when you cast it to another variable type, and so on. If you change one variable type to another, it will change from a negative number to a positive number, from a small number to a big number, and so on. You really have to understand all this, or you'll end up making those mistakes. If strings don't terminate with a null, so longer than expected will cause overflow buffer. Yeah, that's exactly right. You got it, Joe. That's it. It effectively causes a buffer overflow. And the details, it doesn't always have the same effect in every program, but it does mean you're causing memory corruption. You're moving data where it shouldn't be. And then it just depends on the details how you exploit it. Here's, for example, is PHP and MySQL. This was actually from a page, how to make a secure login script. They said, well, you should hash your code with a salt and hash your password, and then compare. If the password matches the saved hash, then the password is correct. And they recommended this, and this is fatal because they have 2 equals there instead of 3. So you're comparing 2 hash values, and what that means is if you have a hashed password like this that contains only, starts with 0E and then has only numbers with no ABC, this is in fact interpreted as the number 10 to the 12 billion, which is 0 times 10 to the 12 billion, which is 0. So this is, all you have to do is find a password with this mathematical property and you will get in. Of course, it's a rare exception. You'd have to have the valid password create one of these hashes, and they're rare, but this is why you shouldn't be doing this, and this is one of the things Arsnake found. A cool security research found quite a few of these things. That's what you get for not using 3 equals signs here. 2 equals means it will interpret, it'll take the password hash, which it'll interpret it as a number, and then it'll translate this one into a number to do the comparison. So it's a lot like that WAT video I played in one of these classes a while back, where there's just many situations where simple statements fail because the language changes the type of the variable from one type to another until you don't understand what's going on. And then there's double free. If you free the same chunk of memory twice, the second free can lead to memory corruption, as it starts trying to fix the pointers from data that's already been gone. And in fact, a chunk that's been sitting there, the next time you free it, maybe you had a chance to write in that data and choose the corrupted data you're going to do with the second free operation. And this is pretty common because you might write code in one part that frees it and there's code in another part that frees it. So a good practice is whenever you free something, set the pointer to null. so it no longer points anywhere valid. So now even if somebody tries to use it, they won't be able to free it again, and they won't be able to use it. So here's an example. You have a pointer that points to memory, and you have another pointer that points to memory. You free one of them, you have the pointer left over. It's called a dangling pointer. So you're left with a handle pointing to an area of memory that is no longer allocated for its old purpose. Another thing you can do, which is similar, is you can use memory without initializing it first. Now, the data section and the BSS section are initialized to 0 on program startup, but the stack and the heap are not. It boots up and they have just random stuff in them left over from previous users of that stack and heap memory. So if you use variables without initializing them, you're going to read data left over from previous function calls. So if you do that, you would think it might lead to an immediate program crash. So you won't find this in the main part of code that get used all the time, but you might find it in like handlers for uncommon errors, situations that don't come up very often, where it might have not been tested. And so here's an example. You allocate some space on the heap here, then you copy some data into there, a function of test, then you free test, and test is never assigned any value. I think the string copy must go from test to data. So the point is you reserved some space and you used it for some function, and then you freed it, but you never defined what was in there. So this function actually operated on random data that was just sitting there. And the point is, how did that data get there? Well, it got dumped in the stack by previous functions, so it's possible that the attacker is able to control that. They might be able to control like a string variable that was written there previously. So it might be controlled by the attacker, and in that case, you got the same thing we did in these heap overflows, where there's a free operation happening on memory that I was able to corrupt. So when it tries to fix the pointer, I get a write operation I can control. And all right. So another thing is if a program uses a pointer after free, because there was more than one pointer to the same memory location, and when you freed one, the other was not initialized, then I can just write to that memory location. And again, I'm writing to a memory location that might be used for another purpose, and I might get code execution. And another one is, of course, race conditions. If you have a program that's something like a server handling many clients, then many people will be using it at once. And if you test it with just one user or a small load, it will look fine. But when it's used by a lot of people at a high load, then there'll be a possibility that you write something to a temporary file and another user changes it, and you come back and read it, it has changed, and your program didn't think of that. That's the sort of thing. If you have a global variable shared by more than one thread and you don't properly lock it, then one user's thread might interact with another user's thread. And these might be intermittent software bugs, and we've talked about this especially in the web design class. This will lead to bugs like you log in and see somebody else's email instead of yours. And it can be exploited in various ways depending on exactly how it works. But this is why modern versions of Linux make all these special temp files with funny file names. Instead of letting you store things in temp, they make special subfolders for each program to try to avoid temp files colliding. But it still does happen. All right, and uh-oh, my mouse is freezing up. Well, let me try closing this Windows machine. Stream is cutting out. That's what I thought, yeah. I'm going to try and decrease the load. My machine started acting funny. Now it's acting better. Let's see, is it okay now? It's looking better. Yep, better. Okay, that's what I wanted. Okay, good. I think closing VMware helped. This would have helped too if it would listen to me. Won't listen to me, all right? Oh, because I closed VMware. Okay, fine. Good. Some people better, some people not better. Okay. Well, I think it'll get better. Okay, good. I don't know what this is. My machine is having these strange freezing problems. It has to do with OBS, I think. All right, let's take a look at a Kahoot. Yeah, good. Yeah, I could tell it froze up here briefly. All right. It seems to be VMware and OBS are incompatible. All right, I'll just keep going. All right, I think that's it. Let's see how it goes. All right, so how do you see data from the stack? That's the format string. We talked about that. You print something without a format string and it reveals random data from the stack. All right, what does stir copy cause? Yeah, the lag is big, but I'm just going to not worry about it. All right, so that's an unbounded copy of memory. There's no bounds checking at all in stir copy. Stir copy copies the first string onto the second string at its full length. You don't control the length. It just copies until it finds the null byte in the first string. All right, and what happens when you have multiple pointers to an object? Yeah, you're likely to have double free. You'll free one, and then you'll free the other. They're both pointing to the same object. All right, what happens when a loop processes several bytes at a time? You skip past the null byte, so you include stuff that should not have been in the string. All right, what happens when one part of the program corrupts another part's data? That's the multi-threaded is the one we talk about. One instance of a program might affect another instance. All right. And what happens when you compare one data type to a different data type? Yeah, those are integer conversions, which can lead to the wrong result. All right. I'm going to assume that's Jordan. I think, although Jordan had a different name often, maybe that's Judy. That's probably Judy. All right. Oh, there's Jordan and Judy. Okay. Good. Then I can disambiguate them. All right. In that regard. Good. All right. All right. Good.